some of the themes of Claudia's talk, although focus more on one particular sort of extension of GR, which is really massive gravity, although that's connected. It's really a family of many things, in fact, as I hope to get across. So when we tend to think about modifications of general relativity, we can categorize them basically into things that change physics at high energies or physics at low energies. So nowadays we tend to refer to things that change physics at high energies as UV, ultraviolet modifications. And the sort of classic examples are string theory fits into this category because we know there's new physics at the string scale. Quantum theory of gravity assumes some new physics coming in at the Planck scale and so on. But there's also other alternatives such as, or not alternatives, but extensions of that. For example, we sometimes imagine there's extra dimensions with possibly relatively large size for the extra dimensions. And so new physics will come in at the scale of the Kaluza-Klein modes of those extra dimensions, and that can end up modifying gravity because then gravity propagates in those extra dimensions. So all of those, though, fit into the notion of ultraviolet modifications where we're changing things at high energy, but not at low energy. And by and large, if you believe Lorentz invariance is fundamental, those types of modifications are well understood in the context of low energy effective field theories in terms of their implications for low energy physics, where we're just basically taking GR and adding higher curvature terms in an effective field theory expansion. Now, that's not the kind of models I want to think about today. I want to think about the opposite kind, which are much more exotic in some sense, which are infrared modifications. And these have been introduced. So this is modifications that change physics at low energies or large distances. And obviously the main motivation for these in the last 10, 15 years or so has been try and say something about why the universe is accelerating as much as it is, or not more. And related to that, the old and the new cosmological constant problems. And also, it's also just to sort of see, how could gravity be different? So it's now we've got all this wonderful data on gravitational waves. If all they're doing is just reproducing what general relativity tells us, we're not necessarily learning that much. So it's more interesting to know, can we put constraints on other theories that may differ slightly from general relativity? Now, the guiding principle in all this is a picture that Claudia took of Steven Weinberg at a conference in Case Western, who was talking about this particular topic. And the guiding principle is what we know is that general relativity is the unique local theory describing local Lorentz invariant theory describing the interactions of a massless spin 2 particle. So that's a particular perspective on what general relativity is that de-emphasizes, if you like, the role of the equivalence principle in space-time curvature and emphasizes the degrees of freedom as what really matters. So the inputs into that is if we assume, as Claudia mentioned, Lorentz invariance locality, massless and spin 2 will lead to general relativity. So in talking about departures from general relativity, we have to give up one of those assumptions. And some people give up Lorentz invariance, some people give up locality. For the purposes of today, I'm going to keep those two particular cherished things, but then what we may have to give up is the masslessness of the gravity, or just the assumption that all you have is a single spin 2. So for example, scalar tensor theories assume you have a spin 2 and spin 0, but you may have other spin 2s. You may have higher spins in some, for example, in string theory. That's effectively what you've got as an infinite tower of spin states. So I'm going to consider this particular possibility, where you give up the masslessness and the single spin 2. And that sort of leads me naturally into the class of theories, and I use that term strictly, it's really a class of theories, which go under the umbrella of massive gravity theories. Now, to talk about what they are, let me just remind you a little bit of field theory terminology. So in quantum field theory, one way to sort of probe a system with some action is to add an external source, as Schwinger introduced, and talk about the generating functional. And that's the generating functional is a nice way of encoding all the correlation functions of a system, but it's basically a way of probing the system by adding an external source, giving it a kick, seeing how it behaves. So for example, in just a free theory where the action is just quadratic, because like box minus m squared, the generating function is also quadratic, and it just looks like an interaction between two sources with the Feynman propagator exchanged between them. So for example, if we write that in momenta space, we have two sources in momenta space, and they interact via the Feynman propagator. And so Feynman diagrammatically, we can think of that as a single boson being exchanged between two sources. Now, in an interacting theory, you don't just have a single Feynman propagator. What you get in the Lorentz invariant theory is essentially a distribution, called something called the Challen-Lehmann spectral representation, a distribution of Feynman propagators with different masses, and that's what you get in interacting theory. So I want to think about it that way. So let's apply that notion to gravity. What is the source in gravity? Well, the source in gravity is the stress energy. So what you get in general in gravity, the generating function, the equivalent of the generating function, is some interaction between two stress energies. If you like, you can think of them as two sources, like the moon and the earth, each one being described by some stress energy. And at leading order, that interaction is described by the exchange of gravitational modes. So in particle physics language, say the graviton, or we can think of it as virtual gravitational waves. It's just a matter of terminology. Now, in general, that exchange, just like in any field theory, can have some kind of spectral distribution. So there may be within that spectrum a pole part, which is an isolated contribution, where you have a particle with a definite mass, which is a stable particle. Now, in general relativity, that's what you have. You have a stable massless particle describing the exchange of the force between two stress energies, and that particle we call the graviton, a massless spin 2 particle. But more generally, you could have a spectral distribution where you include massive states, which come ultimately from interactions in the system. It may be quantum mechanical interactions. You have a spectral distribution, and that can create something that also looks effectively massive. But if it's not a pole, then the state is an unstable resonance-like state. So often then we call that particular situation a soft theory of massive gravity, where you don't have a definite mass, you have a distribution, as opposed to a hard mass where there is really a definite mass state. Now, historically, there was the soft massive theory of gravity was really developed first. And the explicit example is called the Dvali-Gabadadze-Parati model, which was a particular extra dimensional model. And the way it works is in that model, you have an extra dimension, fifth dimension, which is infinite. So all the normal Kaluza-Klein modes, which you get in an extra dimensional theory, which are themselves massive spin 2 modes, rather than having a discrete spectrum, as in the original Kaluza-Klein picture, they have a continuous spectrum. And you can engineer it by putting a particular kinetic term on a brane localized in this extra dimension, so that the distribution of those continuous of Kaluza-Klein modes essentially has a peak at some scale, such that the theory effectively looks like a very soft massive gravity theory with, in fact, the resonance, the lifetime of the resonance is of order the inverse mass scale, but it nevertheless is still as effectively behaves like a massive gravity theory. This, by the way, is a completely covariant theory. It's diffeomorphism invariant in 5D. You can write down an action, which is local, etc., etc. And is the first explicit realization of this kind of paradigm. I'm going to talk a little bit more now about the hard massive case, which was a bit more difficult to construct. And here we can be a bit more guided by how we know, for example, masses get generated in the standard model, which is via symmetry breaking. So we know if we take a theory of particular local symmetry and that symmetry gets broken, essentially what happens is that the bosons that associated the force carriers of the particular local symmetry become massive. Now there's a particular regime, which is a high energy regime in that particular description, where you can use something called the Goldstone equivalence theorem, where you can basically describe the physics of the breaking entirely in terms of the Goldstone modes, which are associated with the symmetry breaking. So let me remind you what that is. It's just a particular model. So think about the abelian Higgs model, where you have your Higgs field as a complex scalar field phi, and you have a U1 gauge field, just Maxwell field, if you can think about it. And so the Higgs field is charged. And so as we know, we're supposed to work with covariant derivatives like this. And the Higgs field being a complex field will shift like a phase under a gauge transformation, and as long as the vector potential shifts in the normal way, then the covariant derivative transforms as it should be. Now, in the symmetry broken state, it's actually nice to split that up and split the VEV of the field up into, and look at the departures from the VEV, and I identify that that's really what is the Higgs boson. Whereas the phase of the field is what you'd call the Goldstone or the Stuckelberg mode. It's the light degree of freedom that gets eaten up by the gauge transformation, and the Higgs boson is the remaining massive propagating particle. Now, there's many different ways to think about this system, but one way to think about it is to go into unitary gauge, which basically fixes the Goldstone mode pi and sets it equal to 0, and then the action for a abelian Higgs model would not look gauge invariant anymore because we fixed the gauge. And the Higgs itself would be a massive particle. And if you're working in energies below the mass of the Higgs, you can integrate it out. And then what the action will look like is basically just the Proctor action, which describes a massive spin 1 particle, plus interactions which are not manifestly gauge invariant. Now, you might say, why did I go through that procedure? Well, the reason I'm going through that procedure is that for gravity, we don't have an explicit, we don't know how to do the Higgs mechanism for gravity, but we do know how to construct the low energy effective theory for the Goldstone mode. And so I'm explaining this procedure in order to say how we're going to do that for gravity. So in the case of the abelian Higgs model, this is what we call the unitary gauge model that you obtain after integrating out the Higgs boson. And you can reverse that process by means of the Stuckelberg trick, which is I can now take this Lagrangian, which isn't manifestly gauge invariant. And if I now perform a general gauge transformation and promote the gauge parameter itself to a field, what I'm actually doing is really just reintroducing the Goldstone mode that I set to 0 and going to unitary gauge. But it has the virtue now that you recognize that A mu is really just itself a kind of effective covariant kinetic term for a scalar degree of freedom, which is the 0 mode of the massive photon that you get in this theory. And by making this form of the Lagrangian is now manifestly gauge invariant. And so now the counting of degrees of freedom and how a massive photon emerges is very clear. F mu, the gauge invariant A mu, is the normal 2 degrees of freedom that you have in Maxwell's theory. And the additional degree of freedom that you have in a massive spin 1 particle, because 2s plus 1 is equal to 3, is explicit now in the Felicity 0 mode. So this Stuckelberg trick that I've just performed, where you take your theory, you go in unitary gauge, and then you undo that gauge transformation and promote the gauge parameter to a field, is a nice way of making manifest the additional degrees of freedom you have in a massive theory in its broken state. And the resulting effective theory actually captures physics in a regime of theories, and in a particular regime, which is captured by what's called a decoupling limit. So specifically, when you're working in energies which are very high relative to the mass of the spin 1 particle, if you take a particular scaling limit where this coupling goes to 0 and the m goes to 0 at the same rate, what you see is that the effective interactions for the Felicity 0 mode or the Goldstone mode, so this is often called the Goldstone effective field theory, take the form of what cosmologists would call a P of X type Lagrangian. So you have non-minimal kinetic terms, and that just arises in the low energy description of the abelian Higgs model. So the reason I've gone through that, as I say, is because in the case of massive gravity theories, we really only know the equivalent of this low energy effective theory description. In order to uncover it, we have to think about what is the symmetry breaking pattern in massive gravity theory. So if you take general relativity, we know the symmetry is diffeomorphism invariance. If you want to give a mass to the graviton, then basically what you're asking is, how do I break the symmetry? How to break the symmetry? Well, what I would like to do is construct a Lorentz invariant theory of massive gravity. And so I want to break the local symmetry in such a way, so I break diffeomorphism invariance, but in such a way that I still leave behind an overall global Lorentz symmetry, or more precisely global Poincare symmetry. So that precise mechanism of breaking is really what's happening is you take the full diffeomorphism group and you have an internal Poincare symmetry, and the symmetry gets broken down to the diagonal one. In the case of bigravity, this is just where if you have two metrics, both have a separate diffeomorphism symmetry a priori, but when you couple them together, that gets broken to the diagonal one, and that's how you generate a mass. So both pictures are just the same. So explicitly how this is achieved as follows. The analog of the VEV of the Higgs field in the spin-2 context, what the analog is itself a spin-2 object, and is essentially what we would call the reference metric. So you need some fixed reference metric around which you define your massive gravity theory. But this reference metric can, by means of the Stuckelberg trick, be written in a covariant diffeomorphism invariant way by simply saying the Stuckelberg trick says I'll do a gauge transformation, which in this case is a diffeomorphism, a general coordinate transformation, and I promote the gauge parameters to fields. So in this case, if I take a metric and I ask how does it transform under diffeomorphisms, it's just this. This is the new metric in the new transformed frame. And then I just take the coordinate transformations, which are here labeled by phi a, and I promote them to fields, and those are the Stuckelberg fields. And in this way, we can construct a theory, effective theory for massive spin-2 particles, which is completely diffeomorphism invariant by means of the Stuckelberg trick. Now, just as in the spin-1 case, making a spin-2 particle massive introduces new degrees of freedom. A massive spin-2 in 4 dimensions has 5 components, whereas a massive one only has 2. So we have 3 new degrees of freedom, and those 3 come in the form of an extra vector, which carries 2, and an extra scalar, which is the helicity 0 mode. And they're essentially naturally built into this field phi, as the vector is just the vector perturbations of that, and the scalar is the ones for which the derivative of the scalar comes in that field. And this is explicitly the helicity 0 mode of the massive spin-2 field. And indeed, you can make this more manifest by, if you take this tensor, which I'm constructing, let's just forget about the helicity 1 modes for simplicity and focus on the helicity 0. By its natural normalization scale for its interactions turns out to be the scale lambda 3, lambda, I call it lambda 3, which is lambda 3 cubed, which is related to the square of the graviton mass times the Planck scale. So if we forget the helicity 1 mode for a second, rather interestingly, a diffeomorphism is naturally a squared thing. Because it's a spin-2, because I have to transform 2 things, I naturally get the helicity 0 mode combination of 2 derivatives of phi in a squared form. So if I want to naturally isolate the interactions of the helicity 0 mode, the natural thing to do is actually take a square root. So I take this now Stuckelberg reference metric, multiplied by the inverse metric, and I take the square root of that combination. That square root combination is exactly proportional to just the double derivatives of the helicity 0 mode. And that plays a crucial role in these theories. In fact, this double derivative of the helicity 0 mode shows you that the helicity 0 mode in massive gravity theories is essentially going to be a Galilean theory. Why? Because if all the interactions enter with 2 derivatives acting on the scalar field, then there is a simple global it's really accidental global symmetry that emerges, which is where if I take pi and I shift by a constant plus something proportional to x mu, v mu, x mu, the double derivative obviously is left invariant by that transformation, because if I do 2 derivatives on x, it goes to 0. So there is an emergent Galilean symmetry in massive gravity theories in which the helicity 0 mode is the object playing the role of the Galilean. And that's how you can see how to construct the consistent interactions in these theories, because we know for Galileans how to write down their, for example, the interactions of them that preserve second order equations of motion. In fact, the simplest way, just for pure Galilean, if you have a scalar field pi and you want to write down all those terms which respect the Galilean symmetry and lead to second order equation of motion, it turns out they're all naturally written down with using the Levy, 2 copies of the Levi-Civita symbol, where I take contractions of the Minkowski metric, double derivatives of the scalar, basically in pairs, AA, BB, CC, DD, and then I multiply overall by pi. And you can, if you work this out, all the contractions, this is just pi box pi. And this is pi d pi squared, the cubic Galilean term. And this is the quartic Galilean, and that's the quintic Galilean term. And there are also natural interactions of the Galilean with helicity, massless helicity 2, where you do the same construction. If you take 2 epsilons and you contract with 2 etas, a single h and 2 dd pi, these interactions are invariant under massless spin-2 gauge transformations for h and the Galilean symmetry for pi, and lead to second order equations of motion. And it's exactly these interactions that naturally emerge in the decoupling limit of massive gravity theories. And so it allows us to infer what the nonlinear Lagrangian has to be. You basically make use of precisely this double epsilon structure, which you get in a determinant. And you can see that all the, and also the fact that dd pi arises from the square root of g minus 1 times a reference metric, allows us to figure out what all the relevant mass terms are that lead to second order equations of motion. And as I say, that in the low energy limit of these theories, the dominant interactions are determined by the helicity 0 mode at a scale set by lambda 3 scale, which is m squared m Planck. And that really that determines most of the phenomenology of these theories. Now, in a general effective field theory, there's in fact no requirement that we should restrict only to operators that lead to second order equations of motion. There are other higher derivative operators that will naturally emerge when we do quantum corrections and so on. But we can very naturally write these down in this language. If the building an effective field theory for massive spin 2, in which the cutoff scale is lambda 3, so the leading interaction scale is this lambda 3 scale, then we would naturally write down an infinite number of local operators with arbitrary numbers of derivatives and powers of curvature and so on, all naturally suppressed by this lambda 3 scale. And because those operators are generally higher derivative, they have less significant impact on the low energy physics, and the low energy physics is dominated by these particular leading terms, which is often called the ghost-free massive gravity terms, or the DOGT Lagrangian. Now, that particular story I've given you is just a particular example, but it's really a generic one. In a generic ion modification introduces new physics. If you want to change physics in the IR, by which I mean cosmological scales, we're introducing some new physics scale m, which typically we take to be of order the Hubble scale today. But in the process of doing that, there's always some intermediate scale between the scale m and the Planck scale, at which something else happens, some other non-trivial physics comes in. And in Lorentz invariant massive gravity theories, this is precisely this lambda 3 scale. The same story I've just said works for bigravity. If you like working with bigravity, where you have 2 metrics, and those metrics are interaction, the same symmetry breaking goes on. You have 2 copies of diffeomorphism symmetry, and they get broken down to the single diffeomorphism symmetry. So you have the same amount of breaking. So you also have to perform the Stuckelberg trick. The natural Lagrangian is basically built out of the same square root structure, just identically. And as I say, because you're breaking the same amount of symmetry, you're breaking 1 copy of diffeomorphisms overall, because you have 2 copies and you break down a single one. You also, in order to capture the additional degrees of freedom you have in a massive bigravity theory, it's also natural to perform this Stuckelberg trick. Although interestingly, it's not clear, because both metrics are dynamical, you have a choice of which one you want to do. You could either do it on the F metric in analogy with what we did before, or you could do it on the G metric. But either way, in the decoupling limit, bigravity also looks like a Galilean theory interacting with 2 massless gravitons. Because if the decoupling limit is defined by taking the graviton mass to 0, such that the helicity 2 modes effectively become massless, but you still have the helicity 0 mode of the massive spin 2 mode, which interacts via Galilean interactions. There are many extensions of this story. Basically, essentially all the Lorentz invariant massive, both soft and hard mass theories look like Galilean theories in a particular limit. In fact, this was recognized already in the DGP model. The Galilean was actually a discovery of the DGP model, which was a soft massive gravity theory. All this does is demonstrate with all the hard massive gravity theories, whether they're a single massive or multiple massive, multi-gravity, whatever you want, they all give rise to Galileans in a particular decoupling limit. I'll skip that. And that brings us to the observational. That was sort of a lightning cursory review of the theoretical construction of these models. But as I say, one of the key features is the emergence of these Galilean fields, these accidental Galilean symmetries, fields which are describing in these theories the helicity zero mode of the massive graviton states. And they interact at a much lower scale than the Planck scale, this λ3 scale, and that's why they control most of the nonlinear phenomenology. So we may ask, what are the constraints on the graviton mass? And that comes from many different sources, many different implications of what giving a mass to the graviton would be. So one thing is, let's say if we give a graviton a mass, eventually you get Yukawa suppression for all the forces. The inverse square law essentially gets cut off exponentially. So some constraints come from that particular aspect. Some constraints, such as the ones from LIGO on the graviton mass, come from the modification of the dispersion relation. Obviously, having a mass for a graviton means that things don't travel exactly at the speed of light, and that has an effect on the overall squeezing of the LIGO waveform. And then the other constraints come from the fact that deep down you have additional degrees of freedom. So because we have these additional helicity zero modes, they can propagate what we'd call fifth forces, additional forces beyond the normal GR1s. And they can also radiate. Because you have additional gravitational degrees of freedom, you can radiate into these additional scalar modes, just like you can in the scalar tensor theory. So I'm not talking about scalar tensor theories per se, I'm talking about theories of massive spin 2, but the end product is that they effectively behave like scalar tensor theories, which the scalar looks like the Galilean, and therefore we can have all these sort of observational constraints on the addition of those things. Traditionally, the strongest constraints on these classes of theories actually come from fifth force bounds, such as lunar laser ranging and so on, as was first noted for DGP and so on. But I'm actually going to talk mainly just for the rest of the time about the extrascalar gravitational radiation. So in order to understand how the physics of these models work, the key thing is to recognize the Weinstein screening mechanism. So Claudia already mentioned that most of these modified theories, they introduce new degrees of freedom, which we don't necessarily see. And so often we need a screening mechanism to explain why we haven't seen them. In these theories of massive gravity, we don't need to introduce a screening mechanism. One is built in, and it's called the Weinstein mechanism because the fact that it was built into massive theories was first recognized by Weinstein back in the 1970s, although how we explain that now is in slightly different language than what he did. And roughly the way this works is as follows. In general relativity, the scale at which the interactions of the helicity 2 mode become nonlinear for a given source is essentially the Schwarzschild radius. That's intuitively obvious, right? If you put a source in a metric, the scale at which the coefficients of the metric become of order unity, depart from, become significant, is the Schwarzschild radius. That's when everything becomes clearly nonlinear. If you're well away from the Schwarzschild radius, then the metric is roughly Minkowski plus a small perturbation. So Schwarzschild radius sets the scale at which the helicity 2 mode become nonlinear. So it's the scale of the interactions of helicity 2 modes. In these massive gravity theories, we have additional states, such as helicity 0 modes. But their interactions are not set by the Planck scale. They are set by this new scale, λ3, which is energetically is much lower than the Planck scale, and therefore is a larger distance scale. And that means that the effective Schwarzschild radius for the helicity 0 modes is something called the Weinstein radius, and it's a hugely much bigger scale. for this. Oh, sorry, I've written it in this picture. It's actually this scale. It's a hugely much bigger scale. It's much bigger than the size. So, for example, for the sun, taking the sort of standard choice of parameters, the Weinstein radius ends up being the size of parsecs. So it's a gigantic scale. So it's a very different phenomenology, because we normally think of, we don't need to worry about Schwarzschild scale physics where gravity spin 2 becomes nonlinear, but we are very much inside the region in which the Lissy zero modes are nonlinear. So if you like, from the point of view of Lissy zero modes, it's like we're inside the black hole in these kinds of theories, because, although it's not quite like being in a black hole, but we are very much in the region where the interactions are Lissy zero mode and nonlinear, and that has to be accounted for in all the phenomenological predictions. Now, the effect of being inside the Weinstein radius is essentially to suppress the contribution of the normal inverse square law in such that the fifth forces are screened, and so they get dropped out. And calculationally, if you just take two static sources and you ask how the static force behaves relative to that in the normal inverse square law force, it gets suppressed. Outside the Weinstein radius, it's approximately 1, but inside the Weinstein radius, it goes to 0 at a particular rate determined by the 3/2 power, at least in the case of cubic Galilean or DGP, the 3/2 power, and goes to 0. And this is the effect of the screening. The fifth forces becomes negligible as we go deep inside the Weinstein radius. And that's why it's so crucial the Weinstein radius is so big, because we are very deep inside the Weinstein radius of the sun. For example, we're at a very small distance relative to the parsec scale, which is the Weinstein radius for the sun. And therefore, the fifth forces due to these additional zero modes are essentially highly suppressed within our local neighborhood. However, we still have these additional polarizations that we can radiate into. And so we still have to check, and this is not less obvious, that we're not radiating into them so much that we can use, for example, the constraints from the Hulse-Taylor pulsar and other pulsars on the spinning down of the orbit, which we know to be beautifully fitting with general relativity. We have to check that we're not radiating into these additional scalar gravitational waves. And to do that, we need to basically, again, account for how the Weinstein mechanism works. So let's imagine now a binary system. Think about the Hulse-Taylor pulsar if you want as an example. So we have a pulsar here, a binary system which is orbiting around itself. The distance that has a particular length scale, the distance between the two objects, which is typically much larger than the Schwarzschild radius for the system. It also has a scale which is set by the rotation frequency. So as they rotate around, they do so at a given frequency. And typically they're non-relativistic, and therefore the scale, the length scale, which is the inverse frequency scale, is parametrically larger than that scale. But in turn, the Weinstein radius for a typical binary pulsar, such as the Hulse-Taylor pulsar, is also hugely much bigger than that scale. So in particular examples, the inverse frequency scale is of order 10 to the 9 kilometers, but the Weinstein radius is order 10 to the 15 kilometers. So because of that hierarchy of scales, we can actually do a reasonable job of trying to analytically compute the scalar gravitational radiation by taking into account the background Weinstein screening and looking at perturbations around that from the source. So the way we do that is, let's just approximate the system by, as we said, in all these massive gravity theories, they look like Galileans in a particular limit in which the Galilean couples to the trace of the stress energy. So as a toy model for that, let's think about the cubic Galileans. We have a scalar field pi with a cubic Galilean interaction coupling to the trace of the stress energy. And let's take the stress energy just to be our binary pulsar system. So it's just a sum of two delta functions along the orbits of the system. And what we'll do is we'll approximate that by an overall total mass located at the center of mass, and then the fluctuations around that. And the total mass, if you like, the total mass of the binary system is the one that creates the overall background Weinstein screening. So what we do is we take the profile of the pi field, the Galilean field, can be taken to be the background field induced by the total mass of the binary pulsar as a source, which accounts for the overall background screening, plus fluctuations around it, which will be time dependent because the source itself is time dependent and orbiting. So the radiation for the scalar modes will be built into this part. This is just a background. However, it's crucial to account for this, to take into account the Weinstein screening. Now, this part you can solve for exactly, given a delta function source, and account for it. And the effective equation for the fluctuations is similar to what Claudia mentioned earlier. Essentially, you get an effective metric. The effective metric determining the propagation of the helicity zero mode, the Galilean field fluctuations, is different than the Minkowski metric, and it depends non-trivially on the background profile. But nevertheless, those fluctuations are coupled to the fluctuations in the stress energy. Now, analytically, you can then go through and compute the power radiated. I'll just skip over the details because it's not too crucial. You can compute the power radiated in that field. And as I'm running out of time, I'll just mention the way we do this. Fortunately, the WKB approximation works well across the Weinstein region. So there's a way we can solve it analytically by matching across the Weinstein region into the region deep inside and the region outside in order to infer the total power. What you get, at least by this analytic approximation, is that the power is dominated, the power in the scalar radiation is dominated by the quadrupole radiation, just like in general relativity. That was not obvious because we're talking about a scalar. Scalars can make monopoles and dipoles, but it nevertheless the case is the quadrupole that dominates. However, if you look at how much radiation in this Galilean field relative to GR, it turns out to be suppressed both by the Weinstein radius and by it's enhanced by the velocity of the system, but suppressed by the Weinstein radius relative to the frequency scale. Now, that analytic approximation can actually be backed up by numerical simulations, which we've done. This is actually for a cubic Galilean system. So this is explicitly what you're looking at is the scalar gravitational radiation induced by a binary pulsar. And you see what that naturally gives is the quadrupole. That obviously looks like a quadrupole signature. That's the quadrupole radiation from that. And when we compute the power in that quadrupole radiation, the numerical for a cubic Galilean, the numerical power fits well with what we expected on our analytic grounds, which is that you get this same, if you remember, there was two factors here. So you get an overall, if you compute it as a function of frequency of the binary system, it goes like 1 over omega to the 5 halves. That's the analytic answer. Numerically, you get more or less exactly that. So it's sort of more or less consistent. So what this is showing, is that the Weinstein mechanism is successful in killing off, suppressing the radiation into the additional scalar gravitational waves in binary pulsar systems, at least for the cubic Galilean. We're currently working on the quartic Galilean, which is a bit more numerically challenged to see if a similar phenomena occurs. Okay, so that was my, I think I've hit my time limit. So that was my sort of lightning review of massive gravity type theories. And the key points is to say that in these, at least if we focus on Lorentz invariant theories of massive gravity, in this broad sense of both soft and hard, what happens is inevitably, if we want to modify gravity in the IR, which is at Hubble scale today, we introduce new physics at an intermediate scale between Hubble and the Planck scale. And in particular, in the Lorentz invariant models, this is usually this lambda 3 scale. A common feature of all these models is in a particular decoupling limit, where a particular range of energy scales, the physics is dominated by the interactions of helicity zero mode, and that helicity zero mode looks indistinguishable from a Galilean theory. You get this accidental Galilean symmetry emerging. Crucially, though, the full theory is not a covariant Galilean or a Horndeski type model. And that's important to stress. The covariantization of a Galilean is not necessarily the covariant Galilean. Massive gravity or DGP model are examples of covariant extensions of Galilean, which are not the same as the covariant Galilean. The Weinstein mechanism really controls most of the interesting phenomenology. and at present it's only relatively poorly understood. It's well understood in the static context, where we can clearly say that fifth forces get killed off in the, say, the Earth-Moon system. In the time-dependent ones, it's a bit more harder to calculate what's going on. So I shall leave it there because I think I've hit my time limit for any questions.